And let's start off with a quick roll call of attendance. So the attendance is definitely decimated. Which I found interesting. Good. Okay, Rachel Berger. Hi. Rena Cement. Hi. Jocelyn Cohn. Okay. Jarl Dannenbaum. All right. Eden Al-Khayyam. Hi. Abigail Goldberg. Hi. Eve Gutloff. Evie, sorry. Elisa Huckley. All right. Elena Hickton. Marcella Homsony, so she told me. Hello, yes, you're online. Okay, good. All right, so you're right there. Okay, perfect. Yes, I hear you. Is what? Excuse me? Oh, okay.
On Zoom. Yeah.
Yes. You're who? Jocelyn? Jocelyn Cohn. Okay. Sorry, I have a second conversation here. Okay. Okay, Shayna, Sarah. Oh, yeah. Hi. Amira Eisenberg. Hi. Jardana Lipson. Hi. Hannah Pupka. Hi. Sissi Schmelzer. Okay. Seema Jäger. Hi. And Elizabeth Zucker. Oh, hi. I will get better with the names and have the corresponding faces. I promise. All right. Okay, very good. So we have that. Good. Okay, today we're continuing, and today we're really starting off now with an actually exciting topic. So we're going to start now into an introduction of here we go again. Last time we didn't figure out how to change that, right? That was the problem, I remember. Sent a few with us for good. Swap this place. Haha. There we go. Okay, good. So we will be talking today about research and statistics, and we're going to get a real introduction into research and design of statistics and research. So essentially, we spoke about it already briefly during last class. So basically, there are two main branches, and essentially it's three. So the two that are listed here, the descriptive statistics, and secondly, the inferential statistics. The third branch, which I believe is worthwhile mentioning, is the planning of research and data collection and statistical approaches. But basically here we have descriptive statistics and inferential statistics. Descriptive statistics is basically the organization and summarization of numerical data that have been collected in research or in routine data collection or in various other ways. So it's basically data that has a certain shape and form, and you have individual records and entries, and you want to organize and summarize those in order to be able to communicate them to somebody else. So you basically want to aggregate all these individual data entries that you have. When you think about, you have 1,000 patients and you have 1,000 different entries of a blood pressure value, you cannot communicate anything of these insights or any of this data to anybody else because it's too many entries. So what you try to do in descriptive statistics, you try to characterize it and you try to describe it in a way that you can communicate it to others. So that's basically the mainstay of descriptive statistics. Whereas the inferential statistics is basically where you try to aggregate data in a way and look at data in a way that you can gain insights from it. Since we talked about blood pressure, the easiest example is that you want to see whether a blood pressure medication has an effect on blood pressure. So you want to see whether there's actually an effect of taking a blood pressure medication and whether it actually lowers the blood pressure. So that's a simple way of looking into inferential statistics. So you want to gain any kind of insights into your data. You want to understand what the dynamic of your data actually is and what your data actually means. So this is inferential statistics. And we're going to talk about the specifics of this later on. So the third branch, and this is the third aspect of it, is planning and design of research and data collection, where actually statisticians inform physicians or clinical researchers or whoever conducts the research on how to actually plan their data collection, how to plan their approaches, and how to plan their research in order for a statistician having good data available to actually do analyses in an adequate format, shape, or form. So these are the three mainstays of statistics. So we talked last time about samples and population. So essentially populations is always a question of definition. So you can have populations of any size, and really your research question will carry the population you actually want to look at. So a population is basically, in broader strokes, in broader terms, is a collection of all possible members in a defined group. So that can be the world population, can be the population in a nation, can be the population of New York or of any other city. So it's a certain defined group where every member is basically part of this population. In contrast to that, you basically also can be looking at samples, and samples is a subset of this population. And the sample as a concept serves as a representative subset of this overall population that will allow for you to gain insights into dynamics of the population. And you're gaining these insights from observing the sample, and this sample will allow you to understand what the dynamic will be in the population. So the sample results are used to estimate the population and the dynamics within the population. And these observations, these individual observations, have a certain kind of format. And there are certain types of variables, quote unquote variables. So if you collect individual entries, so you have like individual blood pressures of each individual in either the population or in your sample, basically all these records together build what is called a variable. And this variable can have different shapes and forms and can take on different forms. It can be converted from one form in another, and it can be used analytically in either form. And we will talk about that. So you basically, you think of two main different forms. One is a discrete variable, and the second one is a continuous variable. So the discrete variable is a variable that can only take on a certain number of values, and you define nominal and ordinal variables. What does that mean? Well, we'll talk about it in a second. Continuous variables are variables that can take on a certain range of values, and we're distinguishing between interval and ratio variables. So when you think of continuous variables, these are basically variables that can take on any value. So when you measure a blood pressure of an individual, you get a certain value of that blood pressure. Now you measure 1,000 blood pressures, you get 1,000 different entries of a blood pressure. So this is a continuous variable because it can take on a certain range, but it can take any value up in that range. And then you distinguish between interval and ratio variables, but we'll talk about this in a bit. Discrete variables, in contrast to that, are basically, you have nominal variables and you have ordinal variables. Ordinal variables are basically variables where you have an order to it. So if you assign now every blood pressure value in your variable blood pressure, which is continuous, a rank, and you say like, this is the individual with the highest blood pressure. This is the individual with the second highest blood pressure. This is the third highest, and up until number 1000 that has the lowest blood pressure. And you have this ranking for each individual. This becomes then an ordinal variable. So it has, in reference to the continuous variable, it has a certain rank, but in its structure, it is ordinal and it's ordered within the framework of the data set. So it becomes by that a discretized ordinal variable that reflects the order within that sample that you're looking at. If you look at a nominal variable, this would be if you would categorize your 1000 blood pressure measurements into certain groups. So you say like, okay, I have this individual that has a blood pressure between 100 and 110. Then I have this individual that has 110 to 120, 120 to 130. So you build groups and you assign each individual to each respective group. So you get, instead of 1000 individual values for each individual, you get blood pressure for the continuous variable. But if you categorize them into groups, predefined groups, you only get a category for each individual. By that, you have created a nominal variable based on a continuous variable. So this is what I meant was converting from one variable in another. So you have a nominal variable that basically stands for a nominal value, like a group name. Then you have the ordinal variable that basically is an order within a system, within a variable. Then you have the continuous variable that is basically an actually measured value that can take on any value within a certain defined range. This is continuous versus discrete. Now let's talk about it in more detail. Any questions about that? Yes. Yes.
So usually when for the like you're just making a chart and a graph and you just organize it in a different way based on if you want to.
Well, if you would look into you would do it in kind of a spreadsheet, right? So you remember how we have in Excel, we have spreadsheets. And if you look into this, for example, so this is the example we're going to be looking at. I'm going to zoom in a bit. I'm going to zoom in a bit as soon as I figured out how. Yeah. Depend? Oh. So here we have, this is the data we're going to be discussing about later. So this is this comes now exactly on the next slide. So here we have IDs, congruent and incongruent. What that means, I'm going to explain in a bit. But you have here continuous variables. These are times. These are times that have been measured, and these are so-called ratio variables. So they can take on any value within a certain predefined range. So this range essentially is then, well, in this case, it's actually infinite because it can take any value from 0 to whatever. But these are continuous variables. So if you would start now to categorize in 0 to 10, 10 to 20, 20 to 30, and you would assign to each entry here only the category, you have created a nominal variable. Whereas this is a continuous variable. As soon as you categorize it, it becomes a nominal variable. Does that make sense? And explain it, but this is how you would essentially depict it. The graphical depiction becomes then more specific because you can depict that on a so-called scatter plot, but we'll talk about this next time. Or you can kind of start categorizing it and depict it more as a histogram, for example. But we'll talk about this later. Does that answer your question? Yeah? Yeah? All right, great. Yes, Edie. Nominal. So nominal is basically where you would try to kind of assign a group to each individual. So if you say, for example, okay, so this is now between 10 and 20, this is between 0 and 10, so you give it a group name. So you say like, these are the guys between 0 and 10. These are the guys between 10 and 20. Is the one with 20? No. Okay, but if it takes longer than 20, you assign it 20 to 30. So you give it a group name and you categorize it based on a feature on their data. Or you can categorize them into male and female, where the male and females have a difference. Also nominal variable, classical nominal variable. Or into any other characteristic. becomes all a nominal variable. Does that make sense? Yeah?
I just thought this is ordinal. So now I don't know.
No, ordinal is if you would order it within the grouping. So you would basically you would assign groups to the individual that would take an order within some certain system that you want to have in your data. So if you would order them, for example, according to the length of time, then you would kind of take an ordinal shape. That would be an ordinal. So it would be an order inherent to the way you would categorize them. So you could make the point that if you categorize them in 0 to 10, 10 to 20, 20 to 30, it kind of has an order, and it kind of is borderline between nominal and ordinal. Yes, but that's going too deep into the conversation already. But essentially, it's group names and groupings, and as soon as there's an order attached to it, it becomes ordinal. Make sense?
Yeah.
All right, great. Okay, any other questions? All right, let's hope this goes back. What's supposed to, yeah, okay. So now we're talking about the Stroop test. So the variables then can take on a range of values, like the reaction time on the Stroop test is essentially the time it takes to say the color compared to the time to say the word. So the Stroop demonstration, so essentially this is kind of a test that is used to kind of test for cognitive functions. So essentially what you have is here 4 colors written out in one homogeneous black color. So you basically read those 4, white, red, green, and brown. You read them fairly quickly, right? It's not that complicated. When it gets tricky is in part 2, where you essentially, well, you can test this, you can test yourself. I don't know whether you've seen the slides now already, but essentially, if you would say now, if you were being asked to say the color of the font after having read already the color as an actual word, this is actually becoming quite challenging, and it will take you longer to essentially make the right statement. So when you look here at green, blue, red, and pink, it will take you longer because you associate with that order in your mind already that there's this order of words. And from that end, you will essentially take longer to really react correctly and state the correct color. So the question is now, why is that actually the case? And there's, it's just the associations that you have drawn to the actual word will inhibit your thinking and association with the actual color. And this is what I meant to show here with this spreadsheet. And this is an example which we will now briefly look at. So I have the data also on Canvas. And this is basically, this is exactly this data that can be found for congruent or incongruent. So congruent is essentially when you read a homogeneous color. So that was the first slide with the colors being stated in black. Whereas incongruent is stating the color of the font, whereas you're actually reading it from a different word. And the reason why I'm showing you this is because these reaction times, these are the continuous variables. And this is already showing you what I meant with descriptive statistics, because what you're trying to do is you're building, by building something like the average. And some of you may, I hope all of you have heard of an average in earlier phases of your education. So an average is essentially nothing else than a depiction of the central tendency within a data set or within a variable. So essentially you do nothing else, but you depict an overall center of this data. So when you think of a certain distribution of data, you will depict by that essentially the center around which the data distributes. So an average is basically the arithmetic sum. So the arithmetic average is the arithmetic sum of all entries divided by the number of entries. So this here can be done with the so-called average function, which essentially is average of cell B2 to B25. And this will calculate the average for you for this variable congruent. Whereas if you build the average between actually B2 to B25, it is actually C2 to C25. And if you actually build the average of incongruent, you can see already that there's a difference between both. So you see that for the congruence, it's 14.1, whereas for the incongruence, it's 22. So there's a clear difference. And we will do a lot, and I'm jumping a couple of slides ahead, because this is already something where you could hypothetically test the so-called hypothesis. Because you could hypothesize that when you test congruent versus incongruent, you will have a longer reaction time with incongruent. And a lot of what we will be doing in this class is actually we will be testing hypotheses. And we will find out how we can test whether a hypothesis actually holds true, a null hypothesis actually holds true, or whether there's actually a significant difference in that data we're looking at. Okay, so this is congruent versus incongruent. If you would start now to essentially zoom in a bit. So now we have ordered the data. So we have sorted the data. So this is now sorted in a descending order. And we have assigned ranks within the group. And this is now an ordinal variable. This is a rank within your sample. And this rank is the ordinal variable you're looking at. If you wanted to categorize it now into a nominal variable, you could hypothetically, this is not the best example, but this is like 0 and 1, would basically you assign a 0 as soon as this is less than 15 seconds of reaction times, or greater than 15 seconds. If it's smaller than 15 seconds, you give it a 1. So what you could say now as a nominal variable, nominal is it has a name that means like these are slow, and you would call this fast, and that would be your nominal variable. That would be a typical nominal variable. Does that make sense? Yeah. I know it's hard. We're all in the same boat. I tried to talk to security that they kind of ramp up the air condition, but that didn't happen. I'm gonna have a conversation with somebody. This is really it's terrible, I know. Okay, any question on that? Or is the Stroop test somewhat clear? It's kind of not too complicated, but it's just important that you have this distinction between discrete and continuous variable well understood. This will kind of haunt you. And you will see the different examples. If you do the sample quizzes, you will see the different examples that Norton and Einstein have in the test bank. Okay, so this is the Stroop test. Okay, so we have talked about categories or name for nominal. Where ranking of data becomes ordinal. We have talked about continuous. We have talked about interval and ratios. So interval and ratios, this is a little bit more of a trickier topic. Interval are equally spaced numbers, which also can take on a negative value. Ratios are like intervals in principle, but they have a meaningful 0. What does that mean? What is a meaningful 0? When you think of the reaction time on the Stroop test, can this take on a negative number? Not really. So that would be a negative, that would be a meaningful, this would be a meaningful 0, where it cannot go negative. So this essentially is a good example. And I also like these examples, and maybe this is a good way to memorize it. So essentially you have a nominal, ordinal, interval, ratio. Think of cookies. Nominal is the name of the cookies. So whether it's a chocolate chip or it's a black and white or whatever cookie you like. Ordinal is the ranking of the favorite cookies. Which one do you like most? Interval is the temperature of the cookie. Because it also can be negative, right? Hypothetically, you could freeze your cookie. Well, I don't know. Well, in some temperature scales, it's a little difficult. In Celsius, like creating the temperature I grew up with, it was easy. And ratios is how many cookies are left from those that you started off with. And I think that's a pretty good way to kind of memorize it and makes it quite logical to think of it in that way. So, well, kind of gave that one away. So what kind of data does the Stroop test give us? So the time is ratio, right? If you rank it, it becomes ordinal. If you group it, it becomes nominal. Yes. Yeah, it's a little. It is, for example, if you think of temperature, it's equally spaced, and it also can take on negative numbers. Whereas ratio is something that basically is a ratio based from something you have at the beginning, a ratio based on something where you have 1 up to something. So it's a little tough to think about. I see that. So it's easier when you think of it in that way. So you can essentially discretize intervals. So you can build certain kind of blocks of it. So it becomes, for example, integer variables where you don't have decimals become classical intervals, whereas ratios are literally every value on its way with that meaningful zero. So mainly the meaningful zero allows you for the distinction between ratio and intervals. So intervals is the broader term in a way. Ratio is a very specific term to something that actually cannot be negative. Does that make sense? Does that address your question? All right. Any other questions? So now we talked about the variables. So what are we doing with the variables? We want to do research with variables. And there's 3 variables, 3 forms of variables that are important in the realm of research. The most important one, and I'm skipping the first one, I'm starting with the one in the middle, is the dependent variable. This is the variable essentially that you measure and that is dependent on your independent variable. So how we're gonna do this the best? Okay, the Stroop test, the reaction time of reading congruent versus incongruent, is something that children that are older than 10 years or older than 15 years do faster as compared to those that are 5 years. Okay, can we agree on that? So age will predict your reaction time on the test. So the older you are, the faster you will be on reading the right colors. Yes, I know a 5-year-old doesn't read that well, but it's not a good example. But basically, age determines the reaction time. Yeah, you have a question? No, reaction time. And this is where I'm getting at. This is where I'm getting at. So age determines the reaction time. By that, the dependent variable is reaction time, and the independent variable that predicts this dependent variable is age. So dependent, reaction time. Independent, age. So essentially, you measure the reaction time, and you know, and you manipulate or you categorize your reaction time based on your independent variable age, where you say like, okay, so that kid was between 5 and 10 and was clearly slower than the kid between 10 and 15. So this is how you look at it. Dependent variable is your outcome, is your measured variable, whereas your independent variable is the one that you actually use to predict your outcome. and you manipulate or you categorize it to essentially go and predict and understand your outcome. Thirdly, you have confounding. So confounding is a little bit of a trickier one, because this is something that you essentially, you want to exclude it because it confounds your thinking, right? It blurs your thinking because it makes you unsure about your association. So you have now an association between reaction time and age. And confounding is something that stands in between and that kind of distracts your clear association that you think you understand it. It's like, okay, older kids are faster in reading these incongruent numbers. And you think you understand this association, but now with confounding, you have something that basically distracts your thinking, blurs your thinking, confounds your thinking. That could be, for example, that one kid is between 5 and 10 years, is hypothetically reading the numbers slower than the older kids, but it did the test already 3 times. So it knew already exactly what it has to read. So obviously it's going to be faster than the other kids, right? As a consequence of that, it will be an outlier in your research and it will confound your thinking because it's an unknown third variable. It's a third influence that confounds your thinking. Does that make sense? You're on board with this? Any questions? So dependent variable is what you measure, is your outcome. Independent variable is what you use to manipulate or categorize to come to your outcome and to understand your outcome. And confounding is whatever is in your association between dependent and independent variable and confounds and blurs your thinking. I think that's a good way to go. Yes. Excuse me?
What's the example for confounding one for the Stroop test?
For the Stroop test, it could be if one participant, 5 years old, supposedly slower in reading, did the test already 4 times. So it knew already what colors it has to read. So it was really, it had a routine of doing the test. So it knew exactly what the thing was about.
It messes up tomorrow.
Exactly. It messes everything up. That's a good way to put it. So it messes up your thinking, right? You thought you have an association, you have a dynamic, and you understand the dynamic, and then some unknown variable comes your way and messes up your thinking. That's the confounder. And confounders are, so you try to control or randomize them away. Okay, we're jumping again, a couple of slides ahead. You essentially, you will do in research, you're trying to randomize people. Okay, that's too early. You're trying to find ways to take confounders out of the equation of your research. So if you compare 2 groups and you want to compare congruent versus incongruent, you want to have that kid that already did the test a million times and knows exactly what it is. You want that kid out. You don't want to analyze this kid. Or if you have 2 kids, you want them balanced between both groups because then it doesn't mess up your thinking, right? So you want to balance. This is how you take a confounding out of the equation. So this is what is meant with randomize it away. But we'll talk about this in a second. So it confounds your other measures and you're trying to control it. You can control it with statistical methods, or you can control it by randomization. The confounders is a big thing, big issue. Yes. Yeah.
So if you're showing someone twice the same order of the colors, it's white, green, blue, red, then you do the second time, but how do you cancel? Like one of the confounding is that they already saw the list.
Exactly. Now, because this is what you essentially do, you randomize orders. You randomize orders, so you try to kind of take all these effects out because they will be confounding your results. So randomizing the order of these colors is an excellent example, essentially, because this is what you do. You randomize sequences, and by that you essentially take such an order bias out of the equation, and you minimize the confounding. Very good example. Thank you. Any other questions? Any other thoughts? If not, then let's carry on. Reliability and validity. A reliable measure is consistent. So reliable is something that you can measure with an acceptable certainty. So if you measure your height today, there's a good probability you will measure the same height tomorrow. Is it always 100%? No, absolutely not. There will be measurement errors with everything that is being measured. Everything on the planet that is being measured will have a measurement error. It's like you buy a car, there's a certain intolerance on the accuracy of how the thing is assembled. There's weights. They have, I don't know, have you heard of the weights that are being stored in Paris? So the original weight, so how much is 1 kilo, has been defined. So that is, I don't know what it's made of. Is it platinum or some really high expensive metal? So they actually have a weight, which is the origin of all weights. So this weight actually is somewhere under a glass lid, and it's the weight. And all the weights on the planet are basically based around this weight. And that's 1 kilo of something. And all scales are being calibrated exactly on that weight. And this is the definition of how much 1 kilo is. And there's a more chemically physical kind of definition, but essentially for practical reason, the calibration is done on that very weight. So there will be always a measurement error, whatever you measure. And it's actually, to be honest, it's actually shocking. Once you find out how much measurement error you actually have for things that you use on a common basis, on a daily basis, the measurement errors, they're tremendous and they're really shocking. So this is reliable. A reliable measurement would be, in principle, consistent. Unfortunately, it's not always, but in a perfect world, it would be consistent. So this is the definition of a reliable measure. A valid measure is one that measures what it was intended to measure. A measuring tape. What else is a measuring tape going to measure than the height, right? So a really good measure, a good variable, is reliable and valid. And the example they're giving here is quite an interesting one. Who of you has ever heard of a Rorschach inkblot test? Yeah? Okay. It's a very interesting test, and I don't know, I just want to quickly show that so everybody has seen it. The Rorschach inkblot test is a test where you see shapes such as these, and you ask the interviewed, your patient, what do you see in there? So in this interpretation serves them the diagnosis of certain conditions, psychological and pathopsychological conditions. So I am not qualified to talk much about this, but you can see that looking at the shape and giving an interpretation of a shape without much input or without much constraints on your interpretation will have some certain limitations in terms of diagnostic accuracy. And this is essentially what happens because it's considerably not valid because nobody really knows what it means and nobody really understands how to interpret it. So all this interpretation of a Rorschach inkblot test do have some certain kind of wiggle room, but again, I don't know much about it. I don't wanna diss a test which I don't understand. But so there are some debates about the validity of the test. But in addition to that, there are some concerns about the reliability. So if you give the same individual another Rorschach inkblot of a different shape, and you try that again like a year later, the interpretation may be a totally different one. So that sheds concerns on the test in terms of validity and also in terms of reliability. So it's an interesting example because it both is questionable in terms of reliability and validity. Any questions on Rorschach implode? Hopefully not too many because it's not my expertise. All right, hypothesis testing. So we talked about this before, right? Congruent versus incongruent. You want to compare both groups. It's basically the same individual did both tests, gave both reaction times. You want to draw a conclusion whether the reaction time was longer for the incongruent assessment. So you want to draw a conclusion about whether there's a relation between variables supported or not by the evidence you have accumulated. So you have measured reaction time and you have now before and after. Before and after two different conditions. So this by its own right becomes a nominal variable. So you have these two groups and you're comparing them and you want to see whether this was really long or not. This testing is called hypothesis testing because your hypothesis says that it will take longer to read these colors when colors and words are incongruent. So this is a specific statistic-based process, and we will talk about this. You will form null hypothesis, and you will form research hypothesis. In broad terms, a null hypothesis is the hypothesis where you assume null difference. So no difference, that's a null hypothesis. So then there's no difference between congruent and incongruent. A research hypothesis is where your actual research question and your alternative hypothesis actually show the difference, and we will talk about the details later on, but yeah. So this is basically hypothesis testing, looking for differences, looking for associations, everything that has a significant influence, a significant difference that really makes a difference and has an effect. Okay, so we spoke about dependent variable, independent variables, and confounders. So now you want to put your variables in a framework and you want to give it an operational definition. So you look into procedures to measure an outcome, to measure a predicting variable or to assess a predicting variable, and to quantify potential confounders. You bring this in a framework of a hypothesis. So you develop a hypothesis and you think about what variables do I need to answer these research questions, or which variables do I have, and what research question could I ask based on these variables that I have. And here's the example for that. So you have an independent variable of pet ownership. So you have 100 people where 50 have a pet, the other 50 do not have a pet. You make them answer a survey about their level of happiness. People that have a pet are happier. So you have a dependent variable is your level of happiness, and the independent variable is your pet ownership. So the question is somebody who owns a pet happier than somebody who doesn't own a pet? So this is basically pet ownership becomes your nominal variable, defining two different groups, pet owner, no pet owner. Level of happiness becomes your ratio variable, your continuous variable, defining whether you are happy or not happy, and how happy are you. So you basically can do hypothesis testing between pet owners and non-pet owners in terms of happiness. Then you have amount of willpower and quitting cigarette smoking. Smokers versus non-smokers, smokers versus former smokers, and the amount of willpower, somewhat quantified with a survey or with any other characteristic. Social media use and how caring people are. Well, that's a longer debate. And same situation, right? So are you, if you're a person caring for others, yes or no, do you have a higher level of social media use? So this is how you operationalize variable for the purpose of testing your hypothesis and asking your research questions and answering your research questions. Does it make sense? Any questions? That's kind of logical, right? It's like this is the train of thought, right? You have an idea, you have a variable, you try to answer a question using your variable, and you basically come to the level. Then you have, in addition to the nominal variable, you also have correlational studies, where you have continuous data, where you basically have where you have continuous data and you do not convert it into categorical data. So you're mapping out healthy behavior as a function of wellness program, the use of wellness program. So essentially, when you have a certain level of healthy behavior, you're more likely to be in a wellness program. Whereas when you have a low level of healthy behavior, you're less likely to be in a wellness program. So this association essentially allows for you to draw conclusions about correlations and associations. And this essentially allows you to find trends within your data. So you can, based on these trends and based on these associations, you can draw conclusions about either of these variables. So if you have somebody with a higher level of with a higher use of wellness program, you can assume that their healthy behavior is going to be higher. If you have somebody who has a low healthy behavior, you can assume that their use of wellness program is going to be lower. So these associations allow for you to also predict one versus the other. And we will do that. We will do that with regression models. It's a lot of fun and very useful. Any questions on correlational studies? No? Then we have the types of research designs. We have experimental designs. And so you have two forms of research. You have experimental design and you have observational design. Observational design is where you, as the name implies, you only observe. Whereas experimental design implies that you are actively experimenting with your participants. So now observational design is usually what we do in my world, for example. We do a lot of data collection based on routine data that is being collected for the purpose of clinical decision-making and clinical observation. So we are going to an institutional review board. We're getting permission to access this data of our patients. And we do statistical approaches, and we're trying to predict and find something out based on this data. But this is observational only, and we don't actively change anything on the therapy and treatment of our patients. If you do an experimental study, you are actually changing something. You're actually changing the treatment. You're changing the therapeutic regimen. You're increasing doses of medication. You are implementing changes to their daily regimen. You, for example, there was the example that is being used here is healthy behaviors. So here's a wellness program. So you have wellness programs in which employees can participate in. And so if you, for example, you would assume that somebody who has access to wellness programs would have a better health outcome, right? So if you allow somebody to join and regularly go to yoga, maybe you have better stress coping skills. So now somebody who has no access to a wellness program may not have as good stress coping skills. So as a consequence, they may have higher blood pressure, classical association. So now the confounder here and the problem that you have to take into consideration with this experimental study where you assign one group to have access to wellness program and the other group to not have access to the wellness program is that if the individual would find or would decide on his participation by his own right, those with a healthier behavior to start with would be more likely to choose to have access to the wellness program. So you would have a bias that they would more likely go into being part of the wellness program. So what you need to do, you need to make sure that your employees, irrespective of the health behavior, are equally balanced between either having access or not having access to the wellness program. Because only when you have this balance, you will have a balanced group allocation. And by that, you will health behavior not have present as a confounder in your data. Because an disbalance in health behavior between those two groups will change and blur your insights. Go back to the Stroop test. You have the Stroop test, congruent, incongruent, 5 to 10 years olds versus 10 to 15 years old. And then you have like the routine kid that basically did the test already 5 times and knows exactly the sequence, how it comes. And the sequence wasn't randomized, as Eden said. So essentially you have a confounder there that basically confounds and blurs your thinking. So health behavior confounds and blurs your thinking. So you need to balance it between both groups. Only then you can draw unconfounded insights into your data. Yes. Yes, exactly. So this would be the intervention, right? The intervention, in your experiment, you have an intervention. You have one change to that individual, to that participant's daily life, which is the access to wellness programs. This is your intervention. The individual can go to have a wellness program, goes to a yoga, I don't know, just like, I don't know, whatever wellness program it takes. So you basically, you have the wellness program, improves the well-being of the employee, and the confounder is the health behavior. So if you have health behavior, if you have in the no access to wellness program, people who like yoga and do yoga already on a daily basis, they will confound your insights. Because now suddenly your intervention that you try to initiate for all your employees is not having that desired effect. So the effect is smaller. The difference to the control group, to this group, is going to be smaller. And that is caused by this as a confounder. And that blurs your thinking and your insight. Make sense? All right, good. Any questions? This is very fascinating stuff, and this is very central and very important, because whenever you think of randomized controlled trials, this is the highest, second highest level of insight in research. Randomized controlled trials, like every drug you have ever heard of, has to go through the FDA to be approved, goes through post-market and post-commercialization phase, assessment phase. All of this is decided based on randomized controlled trials, because only then you can draw insights into how effective is this drug really. Because if you have any confounder in there, you cannot trust your treatment effect. So you need to take these confounders out. Any question on that? Okay, yeah. Causality. Just briefly on that. So we talked about controlling the confounding variables. We talked about the importance of randomization. We want that balance between those confounders. Super important. Experimental studies are the only studies where you basically, to some extent, can make some conclusions about causality. The problem with causality is like no research on the planet will give you 100% insight into causality. So if you have the perfect blood pressure drug and it lowers blood pressure, and you think this is the best drug on the planet, it's like you don't have 100% guarantee on causality, and not a 100% guarantee on causality in every application. So it's only in an experiment you can make what is closest to causality, because with all other research, causality cannot be established with adequate certainty. There are some approaches to it that approximate causality and kind of give you a little bit of certainty about causality, but nothing comes as close as a randomized experiment, randomized studies, which minimize confounding. Yes? Excuse me? It's not manipulating it, it's trying to remove an adverse effect. So in a perfect world, you would study everybody, right? Everybody who needs a drug, and you would just, yeah, you cannot do that. So you only can do a little sample. So you want to have something that informs you about the effectiveness of a drug in a population, but you only have a little sample. You can't study more than a sample. So now essentially that sample needs to be representative of the population. Problem number one. As you can imagine, it's hard to get like a population that really reflects, or get a sample population that reflects the entire population. And problem number two is you need to define your population, and you need to randomize that population. That within your little study, that means to inform about the dynamics in the overall population. There are no differences that are caused by something that you have not thought of. So if you test a blood pressure drug, and we talked about stress coping skills and blood pressure, high blood pressure because of stress coping skills. If you have, for example, in your blood pressure medication group, people who smoke cigarettes, have high cholesterol and don't exercise and don't do any yoga and have high blood pressures, they will be worse if you compare your unhealthy group with, I don't know, with 50 people who are training daily and who are yoga candidates. It's like, so it's hard to compare, right? And this is why this isn't really messing it up. It's just trying to control it and create a controlled setting where you have two comparable groups. And this is also why this is the only setting where you can really draw insights into conclusions on causality, because this is when you see this pure effect of two balanced comparable groups. Yeah, makes sense? Good. Any other questions? All right, so we talked about that. Yeah. So now we have between group designs and within group designs. So this is an easy concept, right? So we have now the blood pressure drugs. Okay, blood pressure between groups. One group gets the blood pressure, one group does not get the blood pressure. It's a between group design. So basically you have two groups and you make comparison between those groups. Within group is the same participant before and after. So you have the individual with no blood pressure medication, then you wait half a year, you give him blood pressure medication, and you wait another half a year, and then you measure his blood pressure again. So you compare within the group. So the individual serves as his or her own control within group design. Any question on that? That's kind of easy. Data ethics. Good. Data ethics is a set of principles related to stages of working with data, research design, data collection, statistical analysis, interpretation of analysis, and reporting of outcomes. So data ethics are super important from many angles. Firstly, it's a question of privacy, data privacy. You're not allowed to access any data that a patient or any individual on the planet is not aware of you accessing it, unless he or she has consented to get that, or unless the data is de-identified that the patient can rest assured that nobody can trace back to him as an individual. So this is a lot of my daily bread, where I basically have like observational studies in large cohorts. It's like if you have 200,000 patients and you pick out one individual and you don't give me the name of the individual, there's no way on the planet I can ever go back. I was like, okay, this is Mr. Smith and he went to the dialysis clinic at 3 p.m. and this is this individual. It's not possible because there's too many people, too much data. So the mass of individuals and the mass of data we have available basically conceals the individual. So you are removing it. You're removing the identity. And based on that, you can do analyses on finding out what the dynamics are. So then you have to design, whenever you do experimental studies, you need to design this in an ethical way. So you can, for example, you cannot withhold medication that you know, and I don't want to go too much into the ethical conversation, but you're not allowed to withhold medication that you know are life-saving, for example, obviously, right? Here in the US, there were the Tuskegee experiments, which were withholding syphilis medication, for example, and this was terrible. It was unethical research was conducted in the 1940s and 50s. So there are many examples where boundaries were just not adhered to and ethics were not complied with. So this is why ethics are super important with clinical research, but also with retrospective and observational research. Its data privacy needs to be adhered to. Analyses need to be independent of age, gender, race, all factors that should not be put any weight on. Data collection should not be something that is being done without the consent of an individual. If you're collecting data solely for the purpose of research, that individual needs to give consent to having this data collected. If it is routine data, then again, we're back to the data privacy question where you can take the identified data to research. But again, overall, it's important that all ethical boundaries are being adhered to. The interpretation and reporting of analyses, same aspect. So it's like you should do ethical analysis. You should try to inform the community, the scientific community, in an unbiased and honest and transparent fashion to make sure that the insights that are being gained from the research are in essence really informing and not being biased in any shape or form and misinforming the community. So all these are very important aspects and lead essentially now to open science, which is essentially an approach encouraging a collaboration and transparency within the scientific community, allowing for a real data accuracy, honesty, integrity of all research and methodology has been conducted, and also promotes the sharing of data, the sharing of statistical approaches, the sharing of codes, statistical codes that have been written in order to understand how things have been conducted. Any questions on that? So issues in psychological science specifically, and I'm not necessarily an expert on psychological science, but the problem are not unknown to the overall field of science. You have data-related problems like replication failures. A replication failure is essentially, so you have a group somewhere in Philadelphia or somewhere in California or wherever that does a research, has a research finding, gains an insight, and then you have another group trying to reproduce that finding and is not able to replicate that very same result. So that's a problem, right? Because now it sheds a rather adverse kind of light on either the initial group or the group that tried to replicate it. So then you go back and forth and like, what could be the difference? What could be the limiting factor? And there are numerous examples where this has happened. So, and this is a huge issue. particularly with studies that are underpowered. Underpowered meaning the sample size, there were not enough subjects studied, or that were drawn from a population that was not comparable. So all these things need to be understood, and replication failures are unfortunately something that happens and something that needs to be understood and investigated, because only once you understand that, you can actually draw conclusions that help you in determining the dynamics in your population. Often found problems are also data collection problems, which is also a problem for many reasons. Can be a problem with the research sampling. From what population have you drawn? What tools have you used? So there are various aspects where this can come into place. Old-fashioned statistics, well, that's a little bit harder to look at, but so there was kind of an evolution of statistical methods. So methods have changed, methods have become better. Does it necessarily mean, so now the findings back in the days weren't necessarily as good? Not necessarily. May have been that there were some things not found that could have been found in the data. Yes, that's possible. So there are just new methods out there that allow now for insights that may not have been possible like a couple of decades ago. Also in terms of processing power. Nowadays you have high performance computers that essentially are much faster, processing much more complex models that would not have been possible 30 years ago. So there was an evolution of things that nowadays we're basically in a better condition and in a better shape to essentially gain insights that may not have been possible decades ago. So these are basically issues that may be found not only in psychology, but generally in science. In terms of data ethics, they have here on the last slide, they have two things. Pre-registration. Pre-registration, when you are conducting, I'm going to show here, when you're conducting research, you're being asked to, whenever you are doing clinical experimental research, when you are doing experimental research, you're being asked to pre-register your research, not only clinical research, also retrospective observational research. For this very reason, because here, for example, so this is a typical way where you can show what study you're trying to do. So this is clinicaltrials.gov from the US NLM, the National Library of Medicine. Basically allows for you to register your study, and there you can actually find all studies that are currently going on. So let's go in my world, let's go in chronic kidney disease. So essentially you will find all studies that are currently going on, and when you review a paper for a journal, you need to check whether this actually was here pre-registered. And here you find all studies that are currently happening all over the world. So you can literally look up whatever study you want to look at. So here, for example, you have chronic kidney disease comparing two drugs in China, in Beijing. So you can rest assured that all randomized controlled trials nowadays are registered on this website. So this is what Nolan and Heinz mean here with pre-registration, because by that you give it a very high level of transparency, because you're saying, okay, so I'm studying this population. I am doing this using this power calculation. I need that many subjects, and I will not do any deviations from that. This is my protocol. This is what I'm doing. This is my study. This is my sample size. This is my population from which I'm recruiting. This is my approach. These are my principal investigators. These are my credentials. So you transparently disclose every aspect that is important for your research and for the community to know. And also, it prevents you from doing what they're labeling here as harking, which I have never heard of harking. Well, I know what harking is, but I've never heard the term. So hierarchy is hypothesizing after the results are known. So I've never heard the term, but I'm well aware that this is being done. So when you have results at hand, you could hypothetically try different statistical approaches until you basically found something that is quote unquote significant, or something that kind of allows for you to report something that is worthwhile reporting. And it is unethical because you should always have a predefined hypothesis, a predefined research question before you start your study. You should not develop your study after you have your results. And once you have the results, it's like, actually, let's do that and let's get that reported. So this is the wrong approach. You should have a predefined hypothesis and research question, then do your research, then do the analysis and report exactly what you intended to do right at the beginning. And this is also why you should be pre-register and not go for hierarchy and develop something after you basically have worked on that. Does that make sense? Yes. Yep.
Psychology and methods, there are a lot of experiments you might do, but if the participants know what the experiment is about, they might change their behavior. I mean, if I'm going to an experiment and I don't know what it is about, like videos or whatever, that's my reaction. But if I know that the experiment is about, I don't know, anger, so I might know in advance and like try to act less anger because I want to look as a better person.
Yes, I absolutely understand what you're saying. And yes, this is a huge problem. This is not only in psychology a huge problem because it's so people change their behavior based on the fact whether they are enrolled in the study. Have you heard of a placebo?
Yes.
Yeah, it's the same reason. It's the same reason because people may have a physiological, pathophysiological reaction just knowing that they're actually taking a study drug. That's why you don't want to have a participant know whether they're taking the study drug or not, because they may change their behavior if they know, like, okay, so I'm taking the study drug. It's like, might as well. Like, I don't know. No, I start smoking again, or something like that, right? So it's you're trying to minimize this effect. In psychology, yes, I agree with you. It's probably behaviorally. It really depends on the research question. So if you ask a research question, you try to ask it in a way that you get an unfiltered, unconfounded insight. That you get an unfiltered, unconfounded insight. So if you ask a research question on anger, for example, and you're trying, I don't know, anger, you're trying mindfulness to curb anger. Okay, so you do mindfulness practices and you're trying to kind of reduce the anger. And would the individual necessarily change their behavior based on that? No, because the anger is triggered by something. So if I don't know how you would, I'm not good in psychological research. How would you test it? Well, it would. Well, you have a recall bias. So how would you quantify anger? You could quantify it with questionnaires. You could quantify it with the individual telling you how often he got angry. You could, anger is a difficult example. Anger is a different, so psychological research also suffers from the outcome, right? So it's like if you want an outcome to be very objective and easily measurable. So anger is not really easily measurable. So that's why I'm struggling a bit explaining that. But I think the placebo effect is kind of the best example I could think of, because if you are essentially giving antihypertensive medication and the individual reacts to that just because he knows he's on that study drug, or changes his behavior because he knows he's not on the study drug, so this is how you try to take it out. In psychological research, it's a little bit harder but behavioral changes are definitely a problem, a huge problem. And this is why you also try blinding, for example. And you blind people to their randomization. So you randomize them in two groups. You don't tell them in which group they are. It goes in the same direction with the placebo, right? You do the same thing. It's like they should not know because they may change their behavior. In psychology, yes, same situation, just different. But yeah, no, it's a good point. It's a very good point. So behavior change is definitely a huge confounder. That's why you try to remove it as good as possible. Good point. Thank you. All right, any other questions? If not, I think we can conclude. It's 7:20. Perfect. Good. I didn't get to the R portion, but I think you forgive me. I'll post a little video. All right. Have a nice evening. Thank you.